Okay, so what we're going to do this week is called the grand title of the standard model of particle physics. And this is what you think of when you think of particle physics, the subatomic. We're going to be using words like quarks and leptons and things during today's lesson. So if you're interested in this kind of thing, then today's the lesson for you. In some A-level specifications, for instance, AQAs, you would spend a very, very long time on this unit of work because it would be something called an optional unit. OCR is slightly different. We don't have optional units with OCR. You do a little bit of everything. So you do a little bit of particle physics and a little bit of cosmology and a little bit of medical physics as well. So if you are Googling about the standard model, or if you do any reading from other non-OCR based textbooks, you will see lots and lots and lots of extra stuff about particle physics. And what I'm going to do today is try and give you a flavor of that, because some of you will be interested in it. So there are lots of things that we're going to go through in today's lesson, which is beyond your specification. In fact, most of what we're going to talk about today is kind of background, interest, and putting it all in context so that you have a proper understanding of what the words mean. Ultimately, this will give you a better understanding of the bit that is examinable, but not everything that you're going to do today is examinable. I'll try and flag what is and isn't as we go through. At the end of at the end of this week's work as well, I'll leave you with some reading to do and some extra work. And I don't know if Mr. Mellings has done it yet, but at some point he will introduce a research pag to you where you have to do a project. Has he done that yet? Yeah, he might have done that. So you might decide that you want to do your research on something based out of today's lesson if you're interested in particle physics. Okay, so it's going to be a bit of a history lesson because it's important to understand where these ideas came from because they're wacky ideas and they don't sound like they should be real. And so it's important for you to understand the long slog that it took a very large number of very intelligent people to get to the slightly crazy standard model of particle physics that we're at now. And it's called the standard model because there are even crazier additions to it that lots and lots of people are investigating and disagreeing on. But the standard bit of the model of particle physics is the bit that everyone agrees is overwhelmingly supported by evidence and is almost certainly true, and therefore isn't contentious. So we're going to restrict ourselves mainly to the non-contentious standard model of particle physics today, and it has a very long history. So we'll go back to the beginning and we'll work our way through. It is covered in the textbook in the tail end of chapter 24, but not much of what I'm going to do with you today is covered in chapter 24. Well, not the first bit anyway. Often when I do this, it takes about a lesson and a half. So I imagine that we won't finish it today, but we'll see how we go. Might be a little bit quicker by screen. Okay, so here we go. So let's put it all in a historical context. And to do that, we need to go back, amazingly, about 2,500 years. So again, this history bit isn't examinable. You don't need to write down Leucippus's name in 500 BC or anything like that. I just want you to have a context for what we're talking about. So Leucippus is one of the what now referred to as the great Greek thinkers from the ancient Greek states. You've probably heard of Plato and Socrates and names like that. Leucippus was one of their contemporaries. So 500 BC is a long time ago. And at that point, obviously the BC, we're before Christianity, but there's still lots and lots of belief in the general concept of God and the supernatural, or gods and the supernatural. And when Leucippus was around, it was the case that if anything occurred, it was because a god made it so. I'm sure you've watched enough films or read enough things about all the Greek gods playing with the pitiful little humans down on Earth. So Leucippus actually broke ground by actually stating that things are the way they are, not because of any supernatural influence, but because of very, very natural influences. So, for instance, he would say that you and I are stuck on the ground because we are made of lots of earth, and the earth is made of earth, and earth sticks with earth, and therefore we are on the ground because earthy things stick to earthy things. Birds, on the other hand, contain a lot of air, and airy things stick with airy things, so the birds are in the air, as are the clouds. Fish are full of water, and that's why they live in the water. So this now seems slightly nonsensical to us, but what you have to appreciate is that he made the huge leap that different objects are all made of the same fundamental stuff, that despite the fact that you and a rock don't look much like each other, you actually have quite a lot in common because you both contain a lot of earth stuff. He called them the elements. So you and a rock have a lot in common because you both contain the earth element. Now, he got the number wrong. We now know that there to be about 120 or so elements. But actually, only 20 of the elements on the periodic table are common in materials on Earth and in the human body. So he went with 4. It's actually more accurately about 20. But that's 2,500 years ago, the very first time in history anybody stood up and said, you know what? Humans and rocks, they have quite a lot in common. They're all made of the same stuff, and they behave the way they do, not because any gods make it so, but because that is their natural state of being. It was radical at the time, and lots of people treated him as a bit of a heretic because he was firmly outside of the sphere of everybody else's thinking. But it was the first moment in history where we would claim that a natural explanation has been given for something that we can't observe directly with the human senses. Big moment in history. So following that big moment in history, 500 years before Christ, we then skip on amazingly 2,300 years before anything else interesting happened, which is just amazing. If you imagine that the year you were born, mobile phones were just getting going, the internet was 5 years old, and social media didn't exist, and you just imagine what has occurred during your lifetime in just that one tiny little sphere, to imagine 2,300 years going by with nothing interesting happening in the sphere of material science is just craziness. So to kind of bend the history a little bit and give you a kind of not quite true version of it, but to give you the highlights of the history, the bottom line is that the Greek states were doing very well. The philosophers were doing their thinking thing for the first time in history. The Greeks had managed to structure a society in which it was possible for a small number of people to spend their days thinking because they didn't have to worry about what they were going to eat. Greek society was based mainly on slaves, which isn't a good thing, but it did mean that the people who weren't slaves were able to think. And so for the first time in history, the human brain was unleashed on something that wasn't survival. And there was this wonderful flourishing of intelligent thought just prior to Christ. And then what happened was that the Romans, lovely as they were, giving us toilets and roads and all the rest of it, they were very practical people, and they liked to build and make, and they didn't really have a lot of time for, well, not at that time, for just pure thought and philosophy. And so when the Roman armies arrived in the Greek city-states and kind of took them by force, they didn't do a lot of preserving of the thought that went on. Libraries got burnt, philosophers got killed, and it wasn't a kind of wonderful absorbing. It was more a trampling in our wake as the Romans went past. But the Romans weren't stupid people, and they realized that if you want to absorb an entire country into your own empire, you need to give them a reason to feel a sense of belonging. And so by absorbing some of the conquered culture into the conqueror's culture, there's a blending of societies which brings a kind of wholeness to the empire. And so as the Romans went through, they absorbed little bits and bobs here, there, and everywhere of the cultures that they took by force. And one of the things that they absorbed from the Greek states was the teachings of Plato. And Plato, much as he is lauded for being intelligent and wonderful and all the rest, he got some stuff wrong. Quite a lot wrong, actually. I mean, wonderful for the time, but like Leucippus claiming there to be 4 elements, and now we know there are not 4 elements, Plato got lots of stuff wrong as well. Things like heavy things fall faster than light things. Plato claimed that to be true, and it isn't, as we have studied. And so what happened was that when the Roman Catholic Church was built as a foundation for Roman society, Plato and Aristotle's thinking was absorbed into the teachings of the Roman Catholic Church. And what that led to was the internalization of some incorrect scientific thought as the word of God. And what that meant was that you couldn't challenge the scientific thought that contradicted Plato and Aristotle without directly challenging the word of God. And that led to claims of heresy and ultimately, eventually, people being burnt at the stake or imprisoned for their whole life. And so the act of absorbing incorrect infant science into the teachings of the church, and then coupled with the power of the church, led to a long period of European history in which scientific thought couldn't occur, because anyone who tried to do it rapidly realized that Plato and Aristotle were wrong, but couldn't publicly say it because the church would squash them. And ultimately that led to the Dark Ages and the scientifically and just the lack of any kind of advance in knowledge, certainly within Europe. And it wasn't until the Renaissance, hundreds of years later, when poets and musicians and artists all started to push the boundaries of what was socially acceptable. And as the arts pushed what was acceptable and redrew the boundaries for where the church was and was not allowed to lay claim to the ultimate say in things, it allowed for people like Galileo to step forward with new scientific ideas and to push those forward. And so it's interesting from a historical point of view why we managed to go 2 millennia without any real scientific thought in terms of material science. But ultimately, all of that is a little bit of an excuse and a little bit of a distraction, because actually, even in the absence of all of that, you have to wonder how quickly artisans would have been able to fashion glass to produce microscopes. That wasn't really held back by anything. And it wasn't really until the microscope got going in the 1600s and 1700s that we really started to have an appreciation of the very small. And so this guy is Dalton. He is Manchester, born and bred. And if you wander around Manchester, you will see plaques like that one on various buildings. That is a building in Manchester. And Dalton was at the university when the university was young, and he made a name for himself as a chemist. And he resurrected this original idea from the Greeks that all materials are made of the same basic stuff. And he came at it from a different perspective. Leucippus had come at it philosophically. Why does stuff fall down or fly? Dalton was coming at it much more practically. When he was doing chemical reactions, he would weigh out a certain number of grams of one material and he would weigh out a certain number of grams of another material. And when he reacted them together, there would always be some of one of them left over unless he got the ratio just right. And so he was working on why it was that chemicals would react together in certain ratios. And ultimately, he was heading towards chemical symbolism and the idea of moles ultimately, and the fact that, you know, carbon dioxide, there's 2 lots of oxygen for every 1 lot of carbon, because they are made of carbon and oxygen, and these are elements that react in certain ratios to each other. So he was much more practical than the Greek philosophers, but the end point was the same, that material is made of small stuff, small indivisible dust, basically, that if you could just you know, when you sand a piece of wood and it turns into sawdust, what Dalton was imagining was if you could carry on sanding the sawdust, you would make smaller and smaller and smaller grains of dust until eventually you would get down to a smallest small piece of dust, the smallest bit of material that you couldn't get smaller than it. The ultimate Lego blocks, basically. And he was a well-read person, and he resurrected the original Greek idea of atoms. Atomos is Greek for indivisible, and he used this idea theoretically, because obviously they're too small for him to have any direct evidence of. He used this idea theoretically to justify that all material is made of the same basic stuff. These atoms might come in a few dozen, he thought. Now we know 120 different varieties, but all made of the same basic stuff. And it's important that you understand that humans have been in their current form, living their lives in societies, farming, building dwellings, living their lives together in their current form for at least 20,000 years. If I could take you back in history 20,000 years, the buildings would look different, the clothes would look different, maybe the language would be a bit different, but people would basically be people 20,000 years ago. And it's important that you understand that in 20,000 years of human history, modern human history, it is only the last 200 or so that have actually seen the concept of atom and a real understanding of the material world around us, which is staggering when you think about it. And it's all going to accelerate a little bit now, because once you breach the threshold of the idea, people start to think. And in Europe in the 19th century, there are lots of people with time on their hands to think. That said, though, we're waiting for the inventors to invent objects. We're waiting for the glass blowers to turn their trade not to ornaments, but to scientific equipment. We're waiting for people to invent electrical cables, which bizarrely is harder than you think it was. The first electrical cables were lengths of copper that were braided because it wasn't possible to make very, very thin pieces of copper. And then they were delivered to the cotton factory so that seamstresses could actually sew cotton thread along the length of the wire because there's no such thing as plastic insulation. So we spend most of the 19th century just waiting for people to invent stuff, just so that we can do scientific experiments. But as the 19th century is coming to an end, Thomson, J.J. Thomson, is finally making some proper, exciting scientific experiments. And although this thing might look unfamiliar, you should see elements of it that you recognize, because we've got one of these in the lab at school. We've used them with you. This is an electron gun. So you can see that on the far right, there's a white screen. That's where the electrons smash in to phosphorescent paint and make little flashes of light when the electrons land there. And at the left-hand side, where it's a bit more teardrop shaped, that's the hot filament that's providing the source of the electrons. So what Thomson did in 1897 was to make something fly across a vacuum inside that glass bottle and hit the screen on the other side. And for the very first time, we had an experiment that demonstrated the passage of an invisible beam of stuff that started in one place and landed somewhere else, way too small to be able to see. And we could deflect this with magnets and other electrical devices. And so it was possible to investigate the properties of these items. And what basically had happened was Thomson had discovered a brand new particle. He'd discovered the electron. He didn't really know what an electron was or how it fitted into the world of atoms, but obviously if atoms are the things that are very, very small, and these electrons are very, very small, then electrons must have something to do with atoms. But 1897, which is only 120 so years ago, that is the very first time in human history that we identified a small particle, smaller than an atom. Okay, you know this guy's name. So in the year 1905, Einstein did something that nobody has matched since. In 1905, Einstein published 3 scientific papers, each of which was capable of winning a Nobel Prize. We've already discussed this a little bit. One of the things that he talked about was an explanation for the photoelectric effect and the existence of photons, which again are subatomic particles, very, very small, and constituents of subatomic matter. He also, as we discussed last week, came up with the idea of special relativity by reinventing our concepts of time and space, energy, speed, acceleration, and force, and gave us the notion that if you travel fast, time slows down and lengths contract, and the concept of rest mass and nuclear energy and ultimately atomic bombs and nuclear power stations. But if he wasn't content with all of that new stuff, reinventing and pushing the world forward, he also turned his attention to a very, very old experiment called Brownian motion. And if we were in school, you'd be doing this experiment right now. Brown was a priest in Scotland, I think, and he was attempting to discover, using the newfangled microscopes that had just become more widely available, he was studying pollen grains because he knew that pollen led to new plant growth, and he knew that at some point life would begin with the pollen. And so what he wanted to see was, where is the moment where God breathes life into the new plant? So he thought that if he observed pollen grains closely enough through a microscope, what he would be able to see, if he was patient enough, would be visible proof of the life force entering the plant through the pollen grain. So he sat for hours and hours and hours watching pollen grain through microscopes. And what he got very upset with was the fact that the pollen grain wouldn't sit still. It jiggled about like crazy. So you need to understand why it's jiggling about, is because when he was observing, he didn't have glass slides with like lovely thin glass cover slips to observe nicely with. The technique at the time was to suspend a bead of water under the microscope and to suspend whatever you wanted to look at on the surface tension on the top of the bead of water. So Brown was actually placing a small droplet of water under his microscope and then dropping a pollen grain onto the bead of water. And what Brown didn't understand, but Einstein did, was that the pollen grain wouldn't sit still because there were billions of water molecules slamming into it every second that were jiggling it about by nudging it from every different direction, constantly causing the pollen grain to wander around on the surface of the water droplet. It was Einstein that realized that what came to be known as Brownian motion, this random wandering of the pollen grain along the water, was able to be analyzed mathematically using statistics. And Einstein did do that analysis, and he worked out that the pollen grain was executing something called a random walk. So a random walk is kind of, if I was a very bad teacher indeed, and I took you into Manchester one evening and got you drunk and then left you in the middle of the square in the middle of Manchester to find your own way home, and you just bumbled about like a drunkard, bouncing off lampposts and fences and buses, and generally randomly walking this way and that for a random period of time, and then randomly changing direction and walking in a different direction for a different period of time, you would execute something known as a random walk. And the key thing about a random walk is, if I felt guilty leaving you in the middle of Manchester, I went back to find you after an hour or so, you wouldn't be there because you'd have wandered off. But I would have the knowledge that the distance you had traveled would be directly proportional to the square root of the time that I had left you for. This distance being proportional to the square root of the time is a kind of consequence of the randomness of the walk, the changing direction at random times for different periods of times in different directions. And Einstein analyzed Brownian motion and discovered that the random walk was taking place for the pollen grains, and therefore he had the statistical evidence that he needed to make the great leap that something was hitting the pollen grains at random intervals with random directions, and that's what was causing the random walk. And he conjectured the existence of water molecules in 1905. And he was doing that on the back of what Dalton had said about atoms. And remember, everyone around this time is starting to think about atoms in a very serious way. So the concept of the atom is very, very real in people's heads. But it's interesting to note that Einstein's 1905 paper is the first direct evidence, observable evidence, of the existence of atoms and particles, molecules, ever. And that was just 115 years ago. Remember, this is in the context of humans doing their modern day thing for 20,000 years. It is only the last 100 or so that we've had any direct evidence for any of this. Okay, thank you to Einstein, but then it gets very quick indeed. So 6 years later, this is just 6 years after the first direct evidence of atoms, Rutherford has dissected the things. You know the experiment he did with his gold leaf and his alpha particles, which again are another subatomic particle coming out of radioactive sources, also unknown what they are, but that hasn't stopped Rutherford from using these tiny little objects and firing them at other tiny little objects to investigate the structure of atoms themselves. So you are familiar with the Rutherford atom, with the central nucleus where most of the mass and the positive charge is, and around that the negative charge, which Rutherford has adopted as Thomson's electrons, discovered just 14 years earlier. So in the context in which we went the best part of 20,000 years without anything at all, then 2,000 years of silence, and then 100 years of nothingness while we invented some scientific experiment devices, we've then in just 14 years gone from not knowing anything at all to actually knowing the structure of an actual atom. As soon as technology comes on board, humans just race forward, and that's been the kind of characteristic of the last 100 years or so, hasn't it? Okay, so Rutherford's got his atom looking a bit like that. But then just 2 years later, a guy called Bohr puts forward the notion that Rutherford's atom needs a little bit of attention to the electrons. And it's Bohr that conjectures that the electrons need to be in certain places. That we've got this shell model where there are, you know, your 288 structure of your electrons. And he's had to do that to explain chemical reactions, and he also had to do that to explain how light interacts with atoms, and how when a photon of light is absorbed by an electron in a shell, it's promoted to a higher orbit. And then when the electron drops back down to its ground state again, or to a lower state again, it releases a flash of light of a very particular frequency. So these are the line spectra that we spoke about at GCSE, and that you'll look at again when we do cosmology later in year 13. And Bohr has had to invent these shell orbits in order to explain all those things. Bohr didn't leave it there, though, and we then enter a kind of disappointing era, which we've already discussed in quantum mechanics, where Bohr needs a way of keeping the electrons in their orbits. And so he invents this notion that the electron, well, he doesn't, but he and his contemporaries developed this notion that the electron is a spread out wave-like object that isn't particularly anywhere, and that if you want to know where the electron is, you have to appeal to statistical probabilities, that it's got an 80% probability of being this distance from the nucleus and a 10% probability of being this distance from the nucleus. And Bohr is pushing on the world this idea that nature is fundamentally statistical and random and probabilistic and not deterministic at all. And certainly, if I taught you earlier this year, I'm not sure if Mr. Downing or Mr. Mellings will have, Miss Gale? Will have told the other class, but we then have this big argument between Einstein and Bohr. So remember, Einstein has invented the concept of the photon and has been the kind of poster boy for heretical, free-thinking, out-of-the-box thought in 1905. But then in less than a decade, Bohr is going even further than Einstein was. Einstein has reinvented time itself and invented the notion of time dilation and nuclear energy and the concept that energy comes in packets. But even Einstein can't get his head around what Bohr is suggesting, that nature is not deterministic, that it's probabilistic and statistical and ruled by the roll of a dice. And Einstein famously screamed at Bohr in a public debate that he was not having any of this nonsense, that God did not play dice with the universe. And Bohr, kind of younger, charismatic, English as his first language, versus Einstein, who's a little bit introverted and shy and likes to think before he talks. In a public debate such as the one they had, the audience firmly fell on the side of Bohr, and Einstein felt embarrassed and demeaned, and he retreated a little bit from public life after that. And Bohr and all of his contemporaries, the next generation, they ran with the idea of quantum mechanics, and science has never looked back. We know that Bohr was right, but Einstein spent the rest of his life trying to prove that Bohr was wrong and to find an alternative explanation for quantum mechanics, which has never been successful. There are still a couple of people around today who are trying to continue Einstein's dream of proving that quantum mechanics is an approximation to a more fundamental, deeper down theory. But in actual fact, on modern theories and modern experiments that have been done in the last 20 years or so, we don't think that's true. We think that Bohr was right all along, and that quantum mechanics is fundamentally correct, that it's a statistical model of what happens, that we genuinely don't know where electrons are or how much energy they've got or what speed they're traveling at. We just know that probabilistically it's within certain ranges. But even Bohr didn't go as far as he could have done. So we skip forward another 14 years ago, 14 years or so, something like that. And we find Dirac. Paul Dirac is a man after Einstein's own heart. Also introverted, also very quiet and shy, doesn't like the limelight, loves Einstein, loves Einstein's equations, loves Bohr's equations, and he's trying to be the bridge. Dirac wants to try to reconcile the ideas of Einstein, which are all about time and space being woolly notions, with the ideas of Bohr, which is all about the location of particles being woolly notions. So in 1927, in a tour de force of mathematics, Dirac creates what is known as the relativistic Schrödinger equation, which couples the ideas of Einstein with the ideas of Bohr and brings a kind of peace to the world of physics in the early years of the last century. And Dirac's relativistic wave equation is celebrated as one of the successes of the last century, up there in the top 10 of greatest achievements of physics. And Dirac investigated the solutions to his equation. It's just an equation with algebra and, times and divides and squares and things like that. It's just an equation. When you write it down, feel free to Google it. It's got some nasty integrals in it, which you might not like. But when you look at Dirac's relativistic wave equation, you ask yourself, well, what are the solutions to it? Just like you know how to solve a pair of simultaneous equations or a quadratic equation, solve it for what the value of x is. Well, Dirac can do similar things with his equation, and he can ask questions like, what is the mass of a proton? And things like that. So he can try to solve his equation. So Dirac sits down and he tries to solve his equation. And it's quite difficult. If you wanted to study the relativistic Schrödinger equation, you would do so in your 4th year of an undergraduate mathematical physics course. So you've got a little bit of education ahead of you if you want to do that. But when you get that far, you can solve his equation. And just to kind of give you an analogy, there is a step towards the end of the solving of the equation, which is analogous to you pressing the square root button on your calculator. What it does is it reveals that there are pairs of solutions to Dirac's equation, that for every positive solution, there is a negative solution as well. And if you hadn't been Dirac and you hadn't been a genius, you might have naively thrown away the negative solutions as just a mathematical aside that doesn't have any meaningful physical reality, and you might just have gone with the positive solutions to your equations. But Dirac was a genius, and he was heavily invested in his equation and what it meant. And Dirac took all of his solutions at face value. And what Dirac discovered was that for every solution to his equation that described a particle like the proton, his equation also described another particle that behaved a lot like the proton. It had the same mass of the proton, but it had a negative electric charge instead of a positive electric charge. Likewise, he had a solution for a particle that behaved like the electron, but he also had a solution to his equation for a particle that behaved like an electron but had a positive electric charge. Dirac decided that these other particles had a physical reality. Now, a bit like Leucippus all those years ago, he got it wrong, we now think, but he introduced the idea that we now corrected and then went with. So Dirac's idea was that the universe is full of a sea of infinite electrons just below the threshold of reality. That quote about there being turtles all the way down, Dirac thought that there was electrons all the way down, and that whenever an electron was visible in the world, it's because a little bit of energy had been given to one of these electrons in the sea of infinite electrons and had liberated one of the electrons into the real physical reality. But what this had done is left a hole behind in the sea of infinite electrons just under our radar of perception. And what Dirac said was that a hole in a solid object behaves a lot like a real object all on its own. So the hole can move around within the sea of infinite electrons. And if an electron were to ever fall back into its hole, the electron and the hole would both disappear from the universe, and the energy that liberated the electron in the first place would be released back into the universe. Dirac called the holes antiparticles, which is an unfortunate term because although it made sense for an antiparticle to be a hole in an infinite sea of real particles, what we now understand from modern day experiments like those that CERN undertakes is that antiparticles are real particles, that the anti-electron is a real particle just like the electron. The only difference between an anti-electron and an electron is that the anti-electron is positive and it doesn't seem to be very abundant in the universe. There are lots and lots of electrons. There are not very many anti-electrons. But if I gave you an anti-electron for Christmas, it would just look like a normal particle. There's no anti to it. There's anti-electrons and electrons, but I wouldn't want you to fall into the trap of believing that an antiparticle was any less of a real particle. It's just not abundant. We just don't see it. But what Dirac did in 1927 was double the number of particles in the universe. Now, to be fair, he doubled it from 3 to 6, so this is no great thing. But we've currently got the electron, the proton, and, well, actually, we don't quite have the neutron at this point, but we have the nucleus. And those 3 particles are explaining all of matter and all of chemistry, and Dirac's gone and invented 3 more that aren't observed in the universe. And this is a little kind of worrying dark cloud on the horizon, that Dirac has just discovered that there are 3 shadowy particles that we've never known about because they don't seem to actually be here. And this is a weird little aspect of our reality that Dirac has just started to leave the door open on. Okay, that's 1927. 5 years later, Chadwick manages to knock some things out of a nucleus, and they're not protons, and they're not charged, so they get to be called neutral protons, neutrons. So that's our 3rd particle from the atom. It took a little while to discover it, but I guess Rutherford and Bohr had predicted its existence. It just took a while for Chadwick to discover it. And then the same year, and you can see how things are accelerating now, Anderson, who's on the other side of the Atlantic to Dirac, and claimed always to be in ignorance of Dirac's work, which he probably was, to be honest, because Dirac was a theoretician at Cambridge and Anderson was an experimentalist thousands of miles away. There's no real reason why one should know of the other's work within a space of just 5 years at that time. Just like Chadwick's just discovered a neutral proton, Anderson's just discovered a positive electron. The image is that of something called a cloud chamber. You take something like a fish tank and you make it very, very, very clean so that there's no dust inside it. And then you fill it with, you supersaturate it with a gas that really wants to condense. We usually use ethanol vapor. So we soak a rag in ethanol, alcohol, and you put it at the bottom of this clean fish tanky thing. And then you allow it to evaporate and fill the fish tank with alcohol vapor. But you keep it very, very cold so that the vapor is below its boiling point. So the vapor really ought to be a liquid, but it can't be a liquid because gases can only turn into liquids if they have a surface on which they can nucleate, where they can clump together as particles. And if you clean your fish tank enough, you can make sure that there's no dust floating around in the atmosphere of the alcohol vapor. And so the ethanol molecules can't actually land on anything in order to nucleate and form droplets. So what you then do is take a source of your new wonderful particles that you're investigating, and you put them against the side of the fish tank, and you let the particles fly into the alcohol vapor. And as the particles collide with the ethanol molecules, they provide nucleation sites for the ethanol molecules to clump together on. And this is what happens in the upper atmosphere when a plane flies through a nice blue sky. Lovely blue skies are often clean air, and there's not much dust up there. And then you send a plane through it, belching out all kinds of nastiness from its engines. And all of this exhaust pollution gases that come out the back of the plane, they provide nucleation sites for the water molecules that are in the upper atmosphere, and they form a cloud behind the plane. And that's what the vapor trail is behind the plane. It's basically evidence that the plane's just belched out a load of nastiness into the air. So that track that you can see in that image that starts at the bottom of the image and curves off to the upper left, that's a particle zooming through the ethanol vapor and leaving a little cloud of ethanol droplets behind it as it goes. That's what the blackness is. And you'll notice it's curving, and it's curving to the left, and that's because Anderson's put a magnet nearby. Magnets make charged particles curve, as we will play with next year when we do electric and magnetic fields. And what Anderson's discovered is that most of the time his electrons curve to the right, but this is a particle that curves to the left. It curves in exactly the same way an electron does, just in the wrong direction. So Anderson gives it a name. It's called the positron, which at least reminds us it's a real particle. It's the only antiparticle, however, that ever got named before people realized what it was. So Anderson got in by naming it. It's called the positron, but actually the positron is just the anti-electron. Later on, we went on to discover the antiproton and lots of other antiparticles, and they all just get called antiproton. They never got named, which is a shame because it makes them sound as if that they are not quite as real as the real particle, which just isn't true. At least when you've got a name, electron and positron, you can see them both as independent particles. However, what is anti about them is back to Dirac's original idea that when they meet, both cease to exist in a process called annihilation. So if an electron ever meets a positron, they're antiparticles of each other. When the positron and the electron collide, both of them disappear from existence and are replaced with E equals mc squared's worth of energy as a photon, actually a pair of photons often. So what we have now got is the concept not just of mass going missing a little bit in a nuclear reaction, but actually this is the full disappearance, 100% of two particles worth of mass, that the entirety of the electron mass and the entirety of the positron mass, 2 lots of mc squared, are liberated into the universe as pure energy. The process is called annihilation. And that is a word that you should be familiar with. It's probably the first word of today that you should be familiar with. Okay, you can see how things have accelerated. You can see how we went all that time without anything at all, and then just between 1897 and 1932, just 35 short years, we have gone from no experimental evidence of any particles at all all the way through to a quantum mechanical model of the atom involving electrons, protons, and neutrons. And now, thanks to Dirac and Anderson, another 3 particles in addition to that seem to be completely superfluous to the world and utterly unrequired. But then it all went crazy. So the war was in the middle and slowed things down a little bit. But over a period of the next 25 years or so, particle physicists started inventing better and better and better machines, taking advantage of annihilation and E equals mc squared. Basically, we invented particle accelerators. We worked out how to make electrons and protons travel very, very, very fast, up to 99% or more of the speed of light. And we took all that kinetic energy and we slammed particles traveling at 99% the speed of light into a target, and we liberated the kinetic energy not as heat. There was so much energy that actually we could make particle-antiparticle pairs. So the kinetic energy would be turned into mc squared times 2 of particles antiparticles. So we would then place detectors around the collision zone, and we would watch the particles come out. And I wouldn't want you to think that we can see these particles. These detectors are akin to cloud chambers. We're basically looking at, you know, what kind of curve trajectory the particles undertake as they pass through our detectors. But over that 25-year history, we got so good at making particle detectors that basically every single time that we turned on a machine, we found a new particle. And it started to become embarrassing because none of these particles appear to exist in the real world. We can get by perfectly well in our universe on electrons, neutrons, and protons. And yet there is just particle after particle after particle raining down on us out of our machines. What kind of a crazy universe do we live in that contains hundreds, literally hundreds of particles that don't actually exist? What kind of a universe is that? And what kind of understanding do we have of the universe if we are only ever seeing 3 particles out of hundreds of it? What is going on in the cores of stars and the hearts of galaxies half a universe away? Are these particles in existence there? Do they have any large-scale influence on the universe? We've been so excited throughout the early years of the 20th century to have discovered atoms and electrons and protons and neutrons, and actually there's a cosmic joke on humanity that we've been so excited to discover 3 particles, and in actual fact there are hundreds of particles out there and we haven't even begun to scratch the surface. And it all just started getting embarrassing. The height of the embarrassment actually comes in 1974, where particle physicists start getting so hung up on the act of discovery without stopping and pausing and wondering what does it all mean, that they're actually starting to fight over who gets to name the particles. So in the same year, experimenters in America discover something called the J meson. I think they had the J. And in China, they've got the Psi meson. And it turns out to be the same particle. And the 2 research groups basically went to war in the press and haranguing each other and publicly having a go at each other like school kids, because they're both trying to claim precedence over who names the meson. And to this day, the Chinese will not call it the J and the Americans will not call it the Psi, or the other way around, whichever way around it is. And so it's always referred to as the J Psi, just to try and keep everyone happy, or possibly the Psi J, I don't know. The experimentalists left the theoreticians just in the dust, basically. And it took a long, long, long time for the theoreticians to catch up, for the successors to people like Bohr and Heisenberg and Dirac, to the next generation to put on their thinking caps and to actually try their best to explain how there can possibly be hundreds of unknown, unwitnessed particles in the universe. What is going on? And I think that's probably a good place to leave it for today. So we'll leave it in 1960. Fresh from the war, science just getting back on its feet. The experimentalists discovered quite a lot, and the theoreticians decided that they're about to take back the physics of the particles. And we'll pick it up on Wednesday with the explanation. Where are all these particles from? Why are they there? What are they? We'll pick that up in a couple of days' time.